So we're group 4, and we'll be discussing a paper called Human Motion Diffusion Model. This was work that was done by researchers from Tel Aviv University in Israel. A little background on the paper. This paper actually has not yet been presented, but it will be this year at the International Conference in Learning Representations, which will take place in Rwanda. As of now, it has around 32 citations, but after the conference, we're sure that that number will only increase, and we provided the links to the paper and to the code right here. So human motion generation, this is prominent in fields like robotics and in gaming, where the focus is on mimicking and recreating realistic patterns of human movement and gait. Text-to-motion generation is a method of performing this task. So for example, given a prompt like this one here, we want to generate a realistic synthetic clip that's in accordance with that. And as we can see, this is pretty realistic and it follows the prompt pretty well. Now, generations like this, they're not that easy to make. And that's because there is a lack of available high quality data to work with. And so for some of the data that is available, we are faced with a data labeling issue. This is where certain words can imply different things depending on the context. This is also referred to as a many-to-many problem. Another issue that we can encounter is the feet shifting problem, where generations don't capture stepping in a realistic manner. So surface to contact with feet isn't really fully captured and more so resembles a sliding effect. The majority of text-to-motion models are either autoencoders or variational autoencoders. And while they are able to learn a shared latent space between natural language and motion, they do so either through a one-to-one mapping or from a normal latent distribution. And both of these approaches are actually inefficient for solving this data labeling issue. So here's a more concrete example of what we mean by this. So if we take the word kick, for instance, this can imply a couple different things. It can imply something like kicking a soccer ball, or maybe performing a Muay Thai kick. What this is that many-to-many problem, which we referred to before. If we approach this even more in depth, we see that this many-to-many problem right here in the form of a little graph. So this word kick, depending on other words in the context, let's say penalty, and maybe we can imagine another word like field, would lead or should lead a model to infer that we're referring to an action such as a soccer kick. And the same applies for a kick with round and Muay Thai. But for reasons that we explained earlier, text-to-motion generators that use either autoencoders or VAEs as a backbone don't have the resources to be able to map a relationship like this. And consequently, this leads to certain scenarios where undesired human actions or movements are generated given some text. But we do know that diffusion models can. They make no assumptions on their targets, and they just iteratively denoise an image until they reach said distribution, making them the perfect solution to this many-to-many problem, and as such for text-to-motion generation. Now, this isn't exactly unexplored territory. There have already been 2 proposed diffusion models for text-to-motion generations, Motion Diffuse and Flame. But what this paper proposes is that compared to the 2 mentioned models, their motion diffusion model can perform text-to-motion generation with higher quality through the use of geometric losses. And consequently, one of these losses actually explicitly addresses the feet shifting problem, which we described earlier, all the while using less GPU resources. Additionally, it is capable of executing supplementary tasks like action to motion generation, where given an input in the form of a scalar, the model will generate an action. So like here we have an input, which is 10, and it generates a sitting action. It could also perform motion editing, which is akin to in-painting. So this could be divided into 2 subtasks, one of them being just editing out a specific body part and making it move in another way. Or we could perform what the paper refers to as in-betweening, which means that if provided with an initial and final set of frames, the model will generate some frames in between. And lastly, it could also perform unconstrained synthesis, which is a form of unconditioned generation. So no generations will occur with no given input. And now I will pass it off to Sanit for the method.
All right, thank you, Ron. Just want to verify, can everyone see my screen?
Yeah, we can see.
All right, thank you. So thank you, Ron. I want to go ahead and start talking about the method behind a motion diffusion model. So our end goal is to generate xt at each step t. So this is pretty much very familiar if you know diffusion models. This is almost the exact same thing. We just want to generate each version at the time step. However, this notation doesn't actually work for our domain of motion. So we need to introduce a new kind of notation that represents something called frames. And we introduce that notation as a superscript up here. So what does this 1:n actually mean? 1:n in this context can be read as a trajectory between frames 1 to n. So now you might ask, well, what is a frame? What is that comprised of? Oh, before I do that, it's the n in that is the number of frames within a motion. So we go from 1 to n frames for a motion, and a motion has, as expected, n frames. So back to a frame. A frame is represented as a matrix of size j by d. So let's talk about what those are. J is the number of joints within the frame. D is the dimensionality of the joint representations. I'm using the specific verbiage here of representation because it can be multiple things. Joint representations can be joint rotations or joint positions depending on the implementer. So this model is actually unique because you're not required to use just joint positions. You can actually choose which data better suits your projected outcome. So if your input data is more rotational, you might want to choose joint rotations instead of joint positions. But ultimately, it's up to whoever implements the model to choose what kind of way their joints are encoded. We'll come back to this because this actually has some effects on loss functions. So I want to kind of visually illustrate what these frames are and how they iterate through. So if we have the prompt, a person performing a kit, we can say that x sub t of frame 1 is just the beginning frame. It's the person standing. That's what it renders to. Then we iterate through every single other frame to generate the motion in between the standing and the kick. So at the end, when we go all the way to the nth frame, we end up with the actual kick. So this is just a visual guide to show you what the frames are and what they represent. Finally, I want to talk about the data distribution that we use to sample for the forward pass of the diffusion model. This is almost exactly the same to a regular diffusion model. However, there's one key difference, and that's that we take frames into account now. So what difference does this make when we run this model? Well, at each step, we go through every single frame and generate every single frame at each step. And this is important to kind of know because it's somewhat of a misconception that at each diffusion step, we go forward one frame. That's not true. We actually go through every single frame in the motion for every single step in the diffusion denoising process or noising process. So it's a semantic thing, but it makes a big difference in how this is computed. So now I want to go over the visual model of a motion diffusion model. So the first thing we do is we do clip text embedding. And we're all familiar with how this works. It was explained in the clip hierarchical image generation paper. So we embed text using clip. And then we take a condition, a provided condition, and we put it through the text through the random mask using that condition. The random mask is just a fancy word for enabling classifier-free guidance for the clip text. Specifically in this paper, they say that 10% of the time, they're going to set the condition to null. So if you remember from clip, if you set the condition to null, it enables it to be classifier free. So that's all this random mask is doing. It's randomly masking some of the conditions in the embeddings. Okay, and then we have our T, which gets sent down to a multi-layer perceptron, and both of these are projected onto a new variable called ZTK. So if we expand out our model a little bit, we have our ZTK here from the previous step. But then, as I implied earlier, we go through every single frame of the motion, 1 through n, and we linearly project that into the same space as ZTK. Now you may recognize this symbol as well. This is the positional encoding symbol, and you can see that they're using sinusoidal positional encoding for this model, and you'll see why in the next step. It's because we're using a transformer encoder. It's the same kind of transformer encoder you've seen in the paper Attention is All You Need. The only difference between this and transformer encoder and that one is that we're not using a decoder. We're only using the encoder part. So we pass our frames and ZTK into the transformer encoder. The transformer encoder does its predictions for each frame once again, because we sent in each frame, and then it skips over ZTK. So these are our prediction frames. And it's worth noting that they're in the same space as the input space. Now you may be asking, why are we using a transformer encoder here? Usually with a diffusion model, we're using something along the lines of a UNet or some variation of a UNet. So why a transformer encoder? Unlike other alternatives like UNet, transformer encoders are more temporally aware. What does that mean, temporally aware? In this context, when I say temporally aware, I mean it's able to take things into context with time, right? So this is important when it comes to the motion domain. Motion and movement are dictated by the amount of time that passes. So at time 0, I might be standing, but at time, I don't know, 50, I might be midway in the air. So time has a huge effect on what the actual joint positions are going to be. So we need to put high importance on it. This is another reason why all frames in a given motion are iterated upon at every time step, because we need to view it all in the same context. We can't view it into different diffusion time step contexts. Finally, I want to talk some more about the transformer encoder, and more specifically the diversity-fidelity trade-off. Canonically, the classifier for transformer encoders, G, we'll reference our transformer encoder as G in this presentation, may lack fidelity and will be overly diverse. MDM mitigates this effect by changing the way that G is sampled. So this is G sub S, where S is the sample. And this is what we're going to use to collect or to sample each of our results from the transformer encoder. So as you can see here, there's no condition, and this enables a lot of diversity because we can technically generate anything without very much constraint. Now I'm going to show the second part. And you can see here we have our conditioned encoder, and then we have our unconditioned decoder. Basically, what this is trying to do is trying to find the difference between the two. And we want to add that to the unconditioned part. What this does is it allows us to get the best of both worlds in terms of diversity and fidelity. It allows us to balance out diversity and fidelity to get the best results, instead of letting one aspect like diversity take over. So finally, the last visual part will be the diffusion process. So the diffusion process, in terms of mechanics, works very similar to the diffusion processes we've seen earlier. There is, however, one major difference, and that's how we send data through each step. So at each step, we have our MDM model, which is the model we just described. And it sends a prediction of each frame. So here, the notation might confuse you because there's no like superscript indicating the frame. However, they omitted the superscript here because they wanted to make it more visually pleasing. But just keep in mind that this is all of the frames, even though it doesn't show up like that. Once we get all of the frames, we simply iterate backwards the reverse process of diffusion until we get our final clean example or predicted example. I also want you to note that these predictions aren't necessarily denoising, right? They're cleaning up, which is slightly different. It's giving you the full dimensionality of each predicted joints in the space, and it's not adding anything extra. So this is another key difference between diffusion models. Diffusion models simply remove the pixel noise, while this one, it returns the clean samples at each iteration point. So I explained how it looks mathematically graphically, but how does this look visually? How does it look compared to a normal noising diffusion model? So this is what a standard image-based diffusion model looks like. You can see that we start off with a bunch of incoherent pixels, and as with t approaches 0, our picture becomes more and more coherent. Now, what does this look like for motion diffusion models? Well, as our t approaches 0, we actually get the cleaner motion, but when it's really high, around 600, it's a bunch of incoherent movements that don't mean anything. So the overarching idea here is similar, it's just the implementation and the representation is a lot different.
Generated images, self-driving cars, augmented reality, virtual reality, it's all around us.
So next, I want to talk about geometric loss. So as I said earlier, diffusion models focus more on the noise aspect of generating images. Motion diffusion models can't use the loss functions found in standard diffusion models because they generate clean samples. So we need an alternative way to determine loss via something called geometric loss functions. The first of the 3 geometric losses is the foot contact loss. Foot contact loss is basically there to prevent the sliding feet phenomenon that other less robust models incur. For example, if I put the prompt a person walking into a less powerful, less robust model without foot contact loss, it does this sliding effect. It doesn't really look like they're walking anymore. It looks more like they're, slipping on ice or something. It's not very accurate and it's not true to life. So we need to find a way to prevent this. And foot contact loss is the way this paper prevents this from happening in their models. So this is the equation for foot contact loss, but we're going to focus on the symbols first that we don't understand, and then we'll expand outwards. So the first symbol that's new here is this F sub I. The F sub I here is the binary contact mass for the foot joints. An example of this I can show is right here. So it's a matrix with obviously 2 possible values, 0 and 1. In my example, it's watered down, so I'll have 1 joint for each foot. So on the left-hand side would be the contact for the left foot, and on the right-hand side, we'll have the contact for the right foot. So if we look at F sub I in different areas, you can see that F sub 1 is where the left foot is not touching the ground, but the right foot is. Similarly, on F sub 4 in the 4th frame, the left foot is not touching the ground and the right foot is not touching the ground either. Next, let's talk about what F sub k means. F sub k represents the core kinematic function. You don't have to worry about the weeds of how it works internally. It's more of a physics problem. However, what you do need to know is that it maps rotational data to discrete joint positions. You may have remembered earlier, I said that a joint representation in this model can be either rotational or positional. And this FK model takes rotational data and converts it to positional data. So what happens if I give this positional data? What does it do? Well, in this case, FK is the identity function. It simply returns the position back, right? So if we give it a rotational frame, a frame with rotational data, it's going to convert that to positional data. If we give it a positional data, it's going to give that positional data back. So either way, we will have positional data. Finally, we take the MSE with an L2 regularizer on the whole entire thing, which is the difference between the position of the next frame subtracted by the position of the current frame. And then we scale this up by whatever we get at our foot contact loss at the ith frame. So there's a lot of math here, but what exactly does this mean for our actual model? How does this actually affect our model? Well, we want to penalize any sample with velocity that occurs on the plane below the foot joints that make contact with the ground. And basically, if your foot is on the ground, in the real world, we have things like friction, and friction prevents us from slipping and sliding everywhere. This whole equation is just a way of advising the model that friction exists when feet are touching the ground and that they can't slip and slide. Next, I want to talk about positional loss, which is somewhat more straightforward than foot contact loss. So I'm going to isolate the meat of the matter right here, and I'll fill in the gaps later. So once again, we have the same FK equation. And regardless of what data we input into this, it's always going to return the positional data of the frame, the ith frame. So we get the positions using FK and we subtract them, similar to what we did before in foot contact loss. And then we apply MSE with an L2 regularizer. So the core difference between this and foot contact loss is foot contact loss only applies to foot joints. It doesn't apply to all the joints in the body, whereas positional loss applies to every other joint in the body. And yes, once again, this is plugged into the MSE equation with an L2 norm. So we have the math. So how does this actually affect the model in the real world? In the real world, we can't teleport from one position to another. Like I can't teleport from inside my house to outside my house. That's not possible. So this loss helps penalize the model by not allowing a figure in the model to teleport to different positions in a plane. So it penalizes things that don't move naturally from one point A to another point B. For the last loss of geometric loss, I want to talk about velocity loss. So here you can notice we're not using FK. And the reason we're not using FK is because we only care about velocity, and the values of either rotational joints or discrete point joints are scaled at the same value rate. So even if we have different values here for different scales, it'll all even out because they're still appropriate for each other. So this is basically saying in the ground truth of the next frame and in the ground truth of the current frame, we're going to get the difference of position or rotation here. Then we're going to subtract that by the ground truth of the, or sorry, not the ground truth, the prediction of the next frame minus the prediction of the current frame. And then once again, just like all the other ones, it's plugged into MSE with an L2 regularizer. Again, so what's the actual impact of this on the model? Well, if I have my arm down and I want to raise it up, I can't do that in a single frame. That's not possible. I can't instantaneously have my arm move. So this helps the cadence of the joint movement and makes sure it's actually natural and not unnatural, where it looks like you're glitching into another space. Your leg is moving without any motion in between it. Finally, I want to talk about the objective. So this model uses a modified version of the standard diffusion model simple objective. And the simple objective from a standard diffusion model is shown here. So in the standard diffusion model, we're more concerned with calculating epsilon. And that's because we're calculating on the noise, and we need to use epsilon to do that. However, in our simple objective, we're not calculating epsilon at all. We're more interested in calculating G, which, remember, G is the transformer encoder. We're more interested in calculating an encoder, which can give us our desired results. So finally, the total loss for an MDM function is each of these individual losses added together. And additionally, we have our cost penalty multiplied with each of our individual geometric losses. So one for position loss, one for velocity loss, and one for foot contact loss. I'm going to go ahead and hand it over to Stefan to talk about the experiments and application.
Thank you, Sunit. All right, so in this section, we're going to cover the experiments and applications of the motion diffusion model. And what the authors did was test their model on 3 motion tasks and 2 motion editing applications here. They trained their model on the NVIDIA GeForce RTX GPU throughout all these experiments with 1000 noising steps and the cosine noise schedule. But before we get started with the experiments, let's address some of the new metrics that will be used to measure the performance of the MDM. There are 3 new metrics, and the first 2 in this slide are R precision and diversity, so for R precision, this measures how well the generated motions align with the input props, and the goal is to just maximize this value whenever it's compared against other baseline models. Diversity, however, is the measure of the variance of the generated motions in all categories. And the goal for this is to produce a value that is closer to the diversity of the ground truth. What does this mean? If you have 2 models and a ground truth, you have models A with a diversity of, let's say, 1.01, and model B with a diversity of 0.9, and the ground truth has a diversity of 1.0, then model A has the closer diversity value, thus making it the better result because its only distance is by 0.01 unit. And so here is the formula for diversity. And so this first variable right here above the summation here is S sub D, which contains 2 subsets of the generated motions, of all the generated motions, and these are randomly sampled. And within this summation, we're going to iterate through vectors. So this first one you see here is V sub I, which is the vector from the first subset. And we're going to subtract that by V sub I prime, which is a vector from the second subset. So we're going to take the magnitude, run the sum, and then normalize it with S sub D. The next metric here is multimodality, and this demonstrates how much the generated motions diversify within each action type. Similar to diversity, we want to have a multimodality that is closer to the ground truth, or the multimodality of the ground truth here. And so here is the formula of multimodality, and there's a new variable called C right here. And basically, it's a set of action types for the generated motions. And then within this additional summation, we're going to basically run the diversity within it. Notice the 2 vectors here from S sub L, which is the same thing as F sub D in the previous slide. And then finally, we're going to normalize it with both C and S sub L. And then another metric used is KID, and it stands for kernel inception distance. And this is similar to FID because it measures the quality of the image. However, it is easier to implement in practice because it's suitable for smaller data sets. And because of this, it produces smaller values than FID. Again, the goal is to minimize the KID, similar to how we want to minimize the FID. And so here's the formula for KID, where MMD is the maximum mean discrepancy of the real images and the fake images squared. So now that we got the metrics out of the way, the first experiment is the text to motion, which is the task of generating motion given input text prompt that Ron described earlier. And this model was compared against 3 other baseline models here, JL2P, text to gesture, and T2M model. And the MDM yielded a state-of-the-art FID score of 0.544, a diversity of 9.559, multimodality of 2.927, and it was on par with other models in terms of R precision, meaning it did not achieve the best R precision score, but it performed really well compared to these 3 models here.
Generated images, self-driving cars, augmented reality, virtual reality, it's all around us.
And so within this experiment, the authors ran 2 additional benchmarks. So this first benchmark here is called the guidance scale sweep. And basically the goal was for us to determine the best guidance scale value. And we can figure that out by looking at the R precision and the FID. And so you can see here around guidance scale sweep 2.5, we found a minimal FID paired with a good maximal R precision. The second benchmark the authors conducted was basically, it was a user study, and they just merely asked 31 users for their preference between their model and other baseline models. And as you can see here, MDM was preferred over 3 of the models that I described earlier. However, the users preferred the ground truth over MDM. Now, although this was the case for MDM, it was still able to yield 42.3% of the users, which is pretty good. The next experiment was the action to motion task, and basically the authors, they gathered 2 data sets for 2 different or gathered 2 sets of results for 2 different data sets. For both data sets, they ran 20 evaluations with 1,000 samples that yielded a 95% confidence, along with a batch size of 64 and a latent dimension of 512. And so for this first data set, they ran 705,000 steps with the Human Act 12 data set. And they compared it against the action to motion actor and INR models here. And the MDM yielded an FID of 0.08, 99% accuracy, classification accuracy here. Second best diversity of 6.86, multimodality 2.58. And then so here is the ground truth values that I mentioned earlier before. Although this is a second best diversity, it's still pretty close to the ground truth diversity, which is really good. This is the leading value of multimodality, and it's pretty close to the multimodality of the ground truth here. For the second data set, they ran 2 million samples with the UESTC data set and compared it with just the actor and INR models, and the MDM yielded a validation FID of 12.81, which is the best amongst the other models that it compared against, and 96% classification accuracy, multimodality of 14.26, a diversity of 33.1. And then here is the ground truth with newer values because of the change in the data set here. So notice the diversity is pretty close to the ground truth. For this final experiment, they ran the unconstrained synthesis, and unfortunately MDM underperformed in all metrics when compared against the MODI model. This was mainly because the authors designed their model to best fit conditional settings more than unconditional settings, so they view the conditional tasks a higher priority than the unconstrained settings here. And so here are the results and how the MODI completely outperformed MDM in the actor model. And notice here, this is the KID that I mentioned before. Notice how it produces smaller values in the FID. And yeah, that's the unconstrained synthesis. And finally, the 2 applications that were implemented for this. The first one that they used was in-betweening, which basically means the authors define a fixed motion or state in the first 25% of the motion and the last 25% of the motion. That leaves the MDM model responsible for the middle 50% to generate. The second application here is body part editing, where you only modify certain joints of the figures here, and the figures labeled in blue is what the model generated, where the person's just taking a step forward. But then when you implement body part editing to change the behavior of the upper body, the lower body behavior is exactly the same as the figures up here. However, the upper body is completely different. So now I'm going to pass it off to Assad.
Oh, thank you, Stefan. Is my screen visible? Just want to make sure.
Yeah, we can see
It is.
Okay, thank you. So we ran our own experiments with the model since the code is open source, and we were able to clone the repository and run the code locally on our machine. And the generation process is executed through this script over here. We need to specify the model path which in this case is the text to motion model. There are other models available as well, like the action to motion and the unconstrained generation, but we limited our experimentation to the text to motion model only. The text prompt is provided over here. As you can see, someone is clapping. And an interesting thing to note here is that there are no hyperparameters being provided in this script. So there's no way to control the generation process, which we have seen previously in some of the other implementations of the diffusion models. And here we see that the clip model is being loaded as Suneet described in the architecture. And finally, there are 3 generations. The model outputs 3 different outputs for whatever text prompt that we have given. So first, we tried a relatively easy prompt, a person doing karate, and the model was able to generate some very realistic looking motions, as can be seen over here. Anyone can tell that this person is doing some kind of martial arts. There is some kind of flying action going on over here towards the end, but overall the generations are very realistic. And one important thing to note is all the generations are very different from each other. Like the movement patterns in them are very different. And that's the main thing with diffusion models is all in the diversity of the generations. Next, we change the prompt to a somewhat difficult task for this model. Someone is clapping, and the generated figures can be seen trying to clap with their invisible hands. But since the model does not have any hand joint information in it, so we can't basically see what it's trying to do. But there is some kind of arm movements going on over here. And finally, we tried a really hard prompt. The person is performing a backflip, and the model fails to generate the complete backflip. But the interesting thing to note is that it looks like someone who is kind of starting to learn how to do a backflip, like you usually start with jumping like this. Okay, you all must be wondering why the output looks like stick figures instead of the humanoid figure that we have seen in the paper. And the answer is that the 3D mesh is generated over the stick figures using a separate script that the authors have provided. This script generates the 3D meshes for each of the frames of the sequence. And when these meshes can be imported into a 3D software like Blender, and they can be used to generate very realistic animations. So moving on to the conclusion, this paper introduces a model for human motion generation, and the architecture is novel in the sense that the previous implementations of the diffusion model have relied on a unit backbone, while this one uses a transformer encoder. And it performed better than some of the state-of-the-art models when evaluated on different criteria, as discussed by Stefan. And the model introduced in this paper is effective for a variety of tasks like text to motion, action to motion, and motion editing. Some points for the paper include that it introduced a novel transformer encoder backbone in the diffusion model architecture, which led to a relatively lightweight architecture, as the authors discussed that they trained the model on a single 2080 GPU, which is a big achievement. And the inclusion of the geometric losses in the training objective, as explained by Suneet, was a very ingenious way of improving the quality of the motion generation. And they use existing data sets and benchmarks, so comparison with all the other models in this domain is very easy and is very straightforward. And another really good thing is that the code is open source. Finally, some points against the paper. The outputs are slightly not as good as being depicted in the paper. The motion is a bit jittery, but overall, the results are really promising. And some of the details of the transformer model are, we can say, are missing. Like they could have added more information about the hyperparameters and the general architecture of the model. And it would have really helped to have some kind of visualizations for the data set as well, since this is a very unique problem with the joints being used for the generation process. Like it would have really helped the paper to have some more information about the joint information. And finally, there's a lack of discussion on how the evaluation metrics like FID have been adopted for this task particularly. The authors do point towards other papers, but it would have been really nice to see some kind of discussion about how the evaluation metrics are being used. Finally, in this section, we want to discuss some ideas that came to us when reading through this paper. And one of the first things that came to us was that the authors state that they use a lightweight transformer-based backbone rather than a unit backbone because the transformer better fits the temporal and non-spatial structure of the motion. But what if we try using the unit backbone, the unit architecture with self-attention layers? As was shown in the latent diffusion paper, they used cross-attention within the unit backbone. So maybe combining the unit with a transformer model could yield much better results. Although it will increase the number of parameters in the model, it might yield result in slower generation, but it could be used to generate much better results. And finally, another idea is basically combining the work by Shah et al. Person image synthesis via denoising diffusion models with this work to generate realistic human motion. So the overall idea is using the temporal pose data from the motion generation model and input it to the person image synthesis model along with the reference human to generate sequence of realistic human motions. So this idea we are looking to explore further in our project as well. So thank you very much, everyone, for listening to our presentation.